continue the class now. In the previous session we were talking about the page replacement algorithms. Okay, we talked about the paging, demand paging, and then why a page replacement is required. Okay, and with what criteria we have to replace the pages. We have seen different algorithms as well. Okay, one of the algorithms is FIFO page replacement algorithm we have seen in the previous session. Now we are remained with two more algorithms, that is optimal page replacement algorithm. Okay, so basically the point to be noted here is it is simply like replace the page that will not be used for the longest period of time. Yani when a page fault occurs and if you want to replace any page and there is no free frame available, we have to replace the page that will not be used for the longest period of time. Getting my point? So let us go to the directly to the numerical here, and you will understand how it goes. Okay, let us say here we have this strings here, a reference string, wherein we are having the request for these pages to be loaded. All right, so first three frames is something like 7. In the first frame it gets loaded. Okay, and next we have the 7 gets loaded into the first frame. All right, next we have 0, and 0 also gets loaded into the second frame. Get my point? 0 gets loaded into the second frame here. Next we have a request for one page, and page 1 will be stored in the frame number 3, which is free frame here. So free frames, no problems here. All right, so as soon as we get the page fault, that page, the demanded page, can be stored into any one of the free frames available here. Okay, so first we stored it in the first free frame, and then second free frame, and third free frame. That's fine. Now we have a request for page number 2 here, page 2, but we don't have any free frames available. Now in this case, which page has to be replaced? Yani either we have to replace 7, or either we have to replace 0, or either we have to replace 1. Okay, so for that thing we have to check in the coming string the pages in the reference string that will be loaded into the pages. Okay, so we have to see the page that is not required for a longest period of time. Get my point? Okay, suppose that, let us say here we have 7, 0 and 1. Among these three we have to replace the page. Okay, let us say 7. Where is it occurring here? 7, it's not here, it's not here, it's not here, it's over here. Okay, but 0 is the next page to be loaded here. All right, and we have another one, 1 is here. So which is far away now? 7 is far away now. Yani 7 is not required, 7 is not demanded here for a longest period of time. So we have to replace the page, which is not required for a longest period of time. That is the logic here. Replace the page that will not be used for the longest period of time. Understood my point? Okay, so here for storing this new page here 2, we have replaced this 7 and we have placed the new page here 2. Got my point, everyone? We have to check all these 3 frames in this string. Okay, and we have to check which page is far away from here, from this point, which page is far away from this point. Now if you look, 0 is here itself, 1 is here, but 7 is very far away. Okay, so we will replace here 7. Understood? Right. Now Next request is 0. 0 is already in the frame. Okay, so there is no page fault here. Okay, there is no page fault for page 0 here. All right, now next request is 3. Is 3 available in the frame? No. Okay, now we have to replace any of these 2 or 0 or 1. Now let us look 2 into this string here. 2 is available here. Okay, and 0 is available next. So 1 is far away now here. Okay, 0 is available here itself, 2 is available next, and 1 is the longest availability here. Okay, so we will replace what? 1 with this 3, right? Okay, next we have the request for 0. 0 is there here already. 0 is available here, so there is no page fault, right? Now next request for page 4. Page 4 is not available here. Now again we have to check this 203 in this list. Which is available first? 2 is available first, then 3 is available first, and then 0 is available. Okay, so 0 needs to be replaced. See, we have to see only those pages which are far away. Only those pages which is far away over here. Okay, so 2 is near here, 3 is near, but 0 is far away. All right, in the third position. So now this 0 has to be replaced with the requested desired page here, that is 4, right? Next request is 2. 2 is here already, right? 3 is already here. All right, okay, so there is no page fault here. Now 0, we have a request for 0. 0 is there here? No, it's not available. Now again we have to check these pages. 2, 4, 3. 3 is available very next. Okay, 2 is available very next, but 4 is not available. 4 is not at all available here. So this 4 will be replaced with the requested page, that is 0. All right, next we have a request for 3. 3 is already available, so there is no page fault. 2 is already available, so there is no page fault. Then we have a request for, this is done, this is done. Now we have a request for 1. 1 is available here? No, it's not available. So now we have to check for 203 here. 2 is available next, 0 is available next, but 3 is not available. So 3 has to be replaced with this 1 here. So 3 has been replaced with the 1. Now again request for 2, which is already there, so there is no page fault. We have 0 here already there in the frame, no page fault. 1 already here, there is no page fault. Now we have 7. 7 is there here? No. Okay, but we have to look 201 over here, right? So for this 7 we have to look 0 and 1. 0 and 1 is here, but 2 is not available. So 2 will be replaced with the requested page here, that is 7. All right, next we have 0, which is already there, 1, which is already there. All right, so in this way the pages will be processed and will be replaced here. All right, now if you look at here the comparison with the previous algorithm, FIFO algorithm, we have less number of page faults here. Now if you look at the page number of page faults here, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Only 9 page faults are occurring in this string, as compared to the same program, the same logic here, I mean the same reference string. If you do it using FIFO, this one, we had more number of page faults. And you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yani almost we have double. We have how many here? Only 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's close to half now. So optimal page replacement is more better than the previous algorithm, that is FIFO algorithm. Understood my point here? Very simple logic here. We have to, if there is a frame here, simply no page fault, and if you want to replace the page, simply look out for the pages that are in the frame in the coming list, and we have to see the page which is at the last. Okay, and that picking up that page, we have to replace that. Understood everyone? Optimal page replacement. Any clarification or any doubt? I'll explain it again if you need it. Easy, good. All right. So shall I move on to the next algorithm? Is everyone clear with that numerical, please? We have 12 students here. Clear. Okay. Even if you are not clear, you can watch it again. Okay, I am recording this video, no issues. All right, quickly moving on to the next algorithm here, LRU page replacement algorithm. Here LRU stands for least recently used algorithm. Okay, so what is being done here? We are replacing the page that has not been used for the longest period of time. Yani, it is the past now. In the optimal, what we were doing, we were replacing the page that will not be used. Okay, but here we have to replace the page that has not been used for the longest period of time. Okay, now this kind of approach is followed in LRU page replacement algorithm. Quickly moving on to the logic here, the numerical. Okay, so 7 is processed directly in the free frame, 0 is processed directly in the free frame, 1 is processed directly in the free frame. Okay, now we have 2. Now which page needs to be replaced here? Okay, so we have to check in the back side. Okay, which page has not been used for the longest period of time. Okay, now here 7 was used in the first. Okay, 0 least used, then 1 least used, more used here. So least used here is what? 7, which is not been used for which has not been recently used for a longest period of time. So 7 is occurring here far away. Simple as that, simple logic here. In optimal, we have to see in the forward direction, but in LRU we have to see in the backward direction. That's it. Okay, the simple logic here that you need to remember. Getting my point? So 7 is occurring in the backward form in the last. Okay, so 7 will be replaced with this new page. All right, now we have a request for 0 which is already available, so there is no page fault here. Then we have a request for 3 which is not in the frame. Okay, so then we have to look for this 2, 0 and 1 in this backward list that has not been recently used. Okay, 0 has been recently used, 2 has been recently used, but 1 which is longest recently used for a longest period. So 1 needs to be replaced here with the new page that is in the third frame, that is 3. All right. Okay, next we have a request for 0. 0 is available in the frame, so there is no page fault. Next we have a request for 4. 4 is here, no. If 4 is not here, we have to check these pages in the backward list. 2 is available here, over here. Okay, 0 very recently used, 3 very recently used. Only what? 2 is recently used for a longest period. Okay, so 2 has to be replaced here. Okay, so then 4 will be replaced by 2. Okay, in the first frame. Now we have a request for 2, but 2 is not in the list. Okay, then again we have to check for these list 403 pages in this. 4 recently used, 0 recently used, 3 recently used. So now 3 has to be replaced with 2 here. Alright, understood? Next we have a request for 3. 3 is here in the frame? No. Then 4 over here, 0 over here, and 2 recently. So which is one? Which is farthest? 0 is the farthest one now. 0 is far away now. So 0 has to be replaced with this 3. Are you getting my point, everyone, please? Very simple logic here. All right. So next we have a request for 0. 0 is available here? No, it's not available. So we have to check for the request which is far away. 3, 2 and 4. So 4 is very much far away here. So 4 will be replaced with this 0. Now we have a request for 3 which is already available here. No page fault. 2 already available, no page fault. Then 3 no page fault, 2 no page fault, and 1. Now 1 there is no frame here, there is no page 1 here. So we have to look for 0 which is very far away, 3 is near, 2 is near. So 0 has to be replaced with this 1. Right. Next we have a request for 2. 2 is already there here, so there is no page fault, right? Then we have 0. 0 is here, no. Then we have to look for these pages here. 2 is recently used, 1 is recently used, 3 is very far away here. So 3 needs to be replaced with 0. Alright, so next we have a request for 1. 1 is already there, no page fault. Then we have a request for 7. 7 is not in the frame. Then we have to look for 102 over here. So 1 is recently used, 0 is recently used, 2 is very far away here. So 2 needs to be replaced with 7. Then we have a request for 0 which is already there, no page fault. Then we have a request for 1 which is already there in the frame. Alright, so we have processed all of the pages here, and if you look at the number of page faults, 1 2 3 4 5 6 7 8 9 10 11 12. So here if you compare with this example, among these 3 algorithms, we see that optimal page replacement is more efficient than all of these algorithms. Get my point? Okay. Right. But if you look at here in the optimal page replacement, it's very difficult to implement. Why is it so? Yani we have to have the knowledge of all the queue, the pages that are needs to be loaded. Yani we don't have that logic, right? Actually, if we have the number of pages in the queue, then it's fine. Yani pages will be loaded dynamically here. So the optimal page replacement algorithm is quite difficult to implement because it requires what? Future knowledge of the reference string. Yani we should know what pages are getting loaded now, what pages are being demanded. Based on those only the optimal page replacement algorithm works. Understood, everyone? Right. At the end of this chapter you have this problems, some list of page strings, page reference strings, and you have the solution as well. So try to solve this, okay? And probably I will send some problems as well as a part of your assignment. Okay, so today I'm gonna upload assignment 2, and probably in the next week I will upload assignment 3 as well. All right. Right. So suppose that we have a term here called as the thrashing. I mean, when this thrashing occurs here, see, last time to deliver assignment 2, it will be 1 week only, please. It only one week, and you have assignment 2 as 10 marks, and assignment 2 10 marks, and assignment 3 20 marks. All right. Why is it not coming here? Assignment 2 10 marks, and assignment 3 20 marks. Is that clear, everyone? And I need clear assignments, please. I don't need the copies. One has done it and simply copied it, the same words, and if you are doing that, you will be losing the marks. Okay, if I found anything which is complete similar, then I will say it as copy. Okay, and I will not give the marks for you. So please try to be optimal here, and try to write your own answers in your own format. Okay, and try to make it more attractive and clear, so that you can gain good marks. More days, not possible. 1 week is enough. We will see, inshallah. We will see. I mean, I may give more than 1 week for assignment 3. Okay. All right. So let us come to the topic here. We have a term here called thrashing. See, in the page replacement topic, we have seen that, I mean, if the program is running and it needs the pages, but the required page, the page demanded is not in the main memory, then what happens? Page replacement occurs, right? Yani the process which is not in the main memory will be swapped out, will be replaced, and the page which is required or demanded will come from the secondary memory into the main memory, right? So this type of activity and is what we call it as a paging activity, right? So if you have more number of page faults, yani high paging activity, okay, then it may have a serious consequences to execute that program. Yani program may go into may take more time for the execution. Okay, so this type of activity is what we call high paging activity, is what we call it as a thrashing. Okay, so we say that a process is thrashing if it is spending more time paging than executing. And instead of doing the work of execution, it is spending more time on the page replacements, yani in the paging. Get my point? Okay, so usually it occurs in many programs here. The thrashing may occur for some programs. Okay, so this is the thing that you need to keep in mind, that what is process thrashing here. A process will be going into the thrashing mode if it is spending more time paging than the executing. Understood? Okay, so this finishes your chapter here. Okay, we have one more topic left, that is disk scheduling, and we have some algorithms as well here, FCFS, and some numericals here. I'm not going into the deep over here. I'll just give you an overview of this in the next class, disk scheduling. Okay, so probably next class I will finish the syllabus, and afterwards I will give you a review of all the topics in the next week.